Hi everyone, I'm Sarmendra Naidu Sivakumar. Today I'll be presenting you with the Microsoft Excel tool for the resource targeting, and in our case I'll be presenting you on the targeting for the low carbon emission with the carbon emission pinch analysis using a graphical method which is known as modified source and demand curve. And this video also provide you with a video demonstration on how to use the Excel tool. Okay, for the modified source and demand curve, which is a graphical method, we have reviewed a journal paper on holistic carbon planning for industrial parks, a waste to resources process integration approach. And for the demonstration purpose, we have chosen a case study on stepwise application of the holistic carbon planning approach to an industrial park centered on a petroleum refinery complex. And this Excel tool mainly focuses on three main steps or methodology, which are number one, extracting data, number two, establishing holistic minimum carbon targets, and number three, designing the minimum carbon distribution network design. And before we go further with the demonstration, let me go through with the Excel tool for better understanding. For this first Excel sheet, which is named direct reuse, we'll be focusing on the two main steps, the step one and step two, which are step one, carbon sources and demand stream data extraction, and step two, to perform targeting the maximum carbon exchange, where we calculate the values to construct the source and demand composite curve. For this Excel sheet, we'll be adding three more steps, which are to plot the source and demand composite curve for the step 3, and for step 4 is to shift the source composite curve to the right so that it touches the demand composite curve and to ensure the curve is feasible. And then for step 5 is to answer the following questions. And now we'll go into step by step in details. So for step 1, which is to perform a carbon sources and demand stream data extraction, we have identified the CO2 sources and the CO2 demands which are planned from the journal review paper. From the paper, we have identified 6 CO2 sources and 4 CO2 demands, which are namely beverage plant, EOR, methanol production, and microalgae cultivation for demand streams, and gasifier, FCC, stack B, stack A, cogeneration plant, and gas turbine for sources stream data. And then we have classified the stream data type and followed by flow rate of the gases and CO2 compositions, which are identified from the review paper as well. Based on the data of the flow rate, which is the total flow rate, and also CO2 composition, we can individually identify the flow rate for the CO2 gases and also CO2 for other gases. And all the units from the review paper is in ton per hour for flow rate. And now for explanation, for CO2 flow rate identification, we can simply multiply the total flow rate with the CO2 composition for each of the data and source streams. And for flow rate for other gases, there are two ways to do it. Either multiply the total flow rate with the remaining composition, which are the composition of the other gases, or to minus the flow rate of CO2 from the total flow rate. And then we use the data from the stream data extraction to perform the targeting the maximum carbon exchange and to calculate the values to construct the source and demand composite curves. Next, for step 2, we just need to use the data extracted from step 1 to fill up the table 1 and table 2. Table 1 representing the values for constructing the demand composite curve, and table 2 representing the values for constructing source composite curve. But you need to make sure of two things before filling up the values. Number one is to arrange the string in decreasing CO2 composition, and number two is just to fill up the data extracted from the step 1 to fill up the table 1 and table 2. And what do you mean by arrange the string in decreasing CO2 composition? It is just basically to arrange the data from highest to lower CO2 composition. For instance, in this case, we have arranged the data from CO2 composition of 99% to 80% to 50% to 10% for demands, and
from 75% to 20% to 15% to 12% to 10% to 8% of CO2 composition percentage for sources. And as I mentioned before, for flow rate of CO2 and flow rate of other gases, we have used the Excel formula where to multiply the total flow rate with the CO2 composition in percentage to find the flow rate of CO2, and you can see the multiplication and divide by 100 if you're not using the percentage. And next is just simply multiply the total flow rate with the remaining other gases composition, or just minus the total flow rate with the flow rate of CO2. And I'm using the second case where I just multiply the total flow rate with the flow rate of CO2. And also we have added the column for cumulative flow rate of CO2 and cumulative flow rate of other gases. We need to find these two values because we're going to construct composite curves based on these two values. And before we fill up the values, we're going to use 0 as the starting point, or the starting values for the both composite curves. And cumulative flow rate of CO2 is identified just by adding or perform summation of the each flow rate of CO2. And same goes to cumulative flow rate of other gases. You can check the Excel formula just by clicking here, which is we perform addition from 0 to 49.5 to get 49.5, and then next is to perform addition from 49.5 and 166.64 to get 216.14, and perform addition of 216.14 with 41.65 to get 257.79, and same goes to the last one. And we need to perform the same thing for cumulative flow rate of other gases, and same goes to table 2. And if you check on to the right, we have simplified the values that needed to construct the demand composite curves line, and also values to construct the source composite curve line. We also use the Excel formula to identify the gradient and y-intercept, and we have identified the gradient and y-intercept to help us later on, which I'll be explaining soon. So based on the values that we have calculated, then we can proceed to step 3, which is to plot the source and demand composite curve line. And for initial stage, we'll be getting the blue one for the source composite curve line and the orange one for the demand composite curve line. If you can see, the both lines are not touching. For our carbon pinch analysis using modified source and demand curves, we'll be touching the source and demand composite curve at 0. So we need to perform some horizontal shift of the source composite curve so that it touches at point 0. It can be done manually, or for this case, we have developed a method to identify the location where we need to shift. This is basically first to identify the pinch point, then just substitute the values into the table. So for first case, identify the pinch point. Based on the curve, we can see that most likely this will be our pinch point, which is this 216.14 and 42.16. So after identify the pinch point, we just fill up the values of the pinch point here, and then find the y-intercept and also gradient, as I mentioned before, using the simple formula, which is from mx plus c formula, and we will be getting the horizontal shift value of 89.66. After getting this value, we need to fill up manually in table 2 to perform the shift to the source composite curve. So let me do it now, which is 89.66. 89.66. And you can see that the source and demand composite curve are touching at one point, which is the pinch point, which is at 216.14 of CO2 flow rate and 42.16 of cumulative flow rate of other gases. And based on these values, now we can proceed to step 5 to answer the following questions. So for step 5, we have 11 questions, each are just simple. We have used the Excel formula to also calculate some of the values as well. So let us have a look one by one. For number of sources, based on step 1, we have identified there are 6 sources, and number of demands, also we have identified 4. Just to quick check. So you can see from here, we have 4 demands and 6 sources streams. And followed with the next question, the minimum carbon emission target and the minimum fresh carbon requirement. From the curve, we can determine these two values. So let us see the guideline to perform or to identify these values. For the minimum carbon emission target is the amount of CO2 flow rate the source composite curve overshoot the demand composite curve above the pinch, which is simply performing subtraction from CO2 flow rate at this point to the cumulative CO2 flow rate at this point. And then for next is to find the minimum fresh carbon requirement is simply perform the CO2 flow rate, which is the amount of CO2 flow rate, the demand composite curve overshoot the source composite curve below the pinch, where we simply perform the subtraction from this point of the source composite curve to the initial point of demand composite curve. And we can also identify the pinch point, which is the point both source and demand composite curve are touching, which is 216.14, 42.16. And we have used some formulas to also key in the values. And then for question number 6 is the what is the carbon emission target before the carbon emission pinch analysis. And question 7 was is the fresh carbon requirement before carbon emission pinch analysis. For these two values, we simply add up the flow rate values, where for the fresh CO2 target, we just perform addition of the flow rate of CO2 from demand composite curve, which is 279.79. And to identify the CO2 emission target, we also perform addition of flow rate of CO2 in source composite curve data, which is identified to be 289.3 ton per hour. And you can see the Excel formula, use the values just to copy paste the values. And then for next question is to identify the maximum possible quantity of carbon exchange. This represents the amount of CO2 flow rate which source and demand composite curve overlap. From here we can see the demand and source composite curve overlap point from this point to this point. And we can simply identify this by performing subtraction of the total emission with the minimum CO2 emission, or subtracting the total fresh CO2 requirement before pinch analysis with the minimum fresh carbon requirement after performing the pinch analysis. And it has been identified that the value is 190.13 ton per hour. And next, for the carbon emission reduction and the fresh carbon requirement reduction in percentage, we can identify this by simply using the formula in the guide given, where we just divide the flow rate of CO2 exchange by the flow rate of CO2 of the source before performing the pinch analysis, and CO2 flow rate exchange divided by CO2 flow rate of the demand before performing the pinch analysis for the fresh carbon requirement. And then for last question, the feasibility calculation. For this Excel sheet, we recommend the the design if the reduction is more than 20% or based on the company decision. And this is just for this Excel. In actual case, it's supposed to based on the company decision. And that's for the first step. Before we continue with the next step, let me review on the carbon management hierarchy, which is in the next section. Okay, for the carbon management hierarchy, we have identified there are 4 levels, starting with the direct reuse as the top priority, followed by source and demand manipulation, followed by regeneration reuse, and followed by carbon sequestration. So we cannot perform source and demand manipulation first, then we use direct reuse. And for this case, for upcoming tutorials or demonstration, we'll perform for H1, H2, H3, and H4. And what are these? H1 basically heuristic 1, above the pinch, apply process changes to eliminate or to reduce carbon source streams. H2 is to increase the limiting flow rate or to add new demand processes above the pinch. And H3 is to reduce or eliminate demand processes below the pinch. And H4 is to regenerate source stream across the pinch to achieve purity higher than the pinch purity. And that's all for the review on carbon management hierarchy. Now let us look for the H1 in next Excel sheet. So what we have performed in earlier demonstration, it will be representing the level 1, which is the direct reuse. Now we'll focus on level 2 H1, which is the above the pinch, applying process changes to eliminate or reduce carbon source streams. Okay, there are two actions taken for the case study in the journal review paper, which is number 1, to use biomass or solar for the source number 5, and this will reduce the flow rate and CO2 emission by 20%. And also to use biomass or solar for source number 6 and to improve the combustion efficiency. This will reduce the CO2 composition to less than 5%, which will be less significant. So source 5 will be not considered anymore as a significant source to perform the carbon emission pitch analysis. So we will remove the source number 6. Now we're gonna perform the same steps we performed for the direct reuse just now in earlier demonstration, where we're gonna extract the data, fill up table 1 and 2, plot the composite curve lines, and then shift the source composite curve so that it touches at the pinch point, and also answer the questions below. But based on the information given, there will be a slight changes to the values. So that one I'll be showing in this video, where from 200 we multiply with the 80%, we'll be getting 160, and also reduction of flow rate, where 10 multiplied by 80% will get 8% of CO2 composition. And we also remove the source number 6 shown below. And by performing this, we'll be having some reduction in the minimum carbon emission target, but the fresh carbon requirement maintains the same and the pinch point maintains the same. And for level 2 H2, where we'll be doing manipulation for the demand, where we increase the limiting flow rate or add new demand processes above the pinch. And for these cases, we also identify two scenarios where the methanol production can be maximized to 200 ton per hour, and for microalgae cultivation can be maximized to 250 ton per hour. So by performing these two changes, we can change the flow rate, which is the total flow rate, from 83.3 to 200 and 220 to 250. By performing this, we'll be getting a new composite curve line as shown here. And when we see the step 5, the fresh carbon requirement still maintain the same and the pinch point is also the same, but the minimum carbon emission target F reduced to 23.42. So this shows that a good improvement in reducing the CO2 emission more. And for next step, level 2 H3, which is to reduce or eliminate demand processes below the pinch, we have identified from the journal paper that uh, demand source 1, the demand 1 will be eliminated as it requires expensive food grade and fresh CO2. So by removing the demand 1, we'll be getting a new composite curve line as shown in the Excel here. And for now, we'll be getting a new fresh carbon requirement of 40.66, but there's a slight increase in minimum carbon emission target. This is due to change in the pinch point location. But still, the reduction of the carbon emission is about 90%, and reduction of fresh carbon requirement is 85%. Following for the H4, level 3 H4, which is to use regeneration or reuse, where it regenerates the source stream across the pinch to achieve the purity higher than the pinch purity. But in this case, we're gonna use the source S5 to increase the purity above 99%, and thus by increasing the percentage, now we can see that in the table we'll be having the cogeneration plant at the topmost value because that's the highest CO2 composition. So now by performing this Excel calculation, we'll be getting a new composite curve line as shown here, and also the reduction is up to 95.45%, where the new minimum carbon emission target is 12.50 ton per hour. And also this shows the overall summary from the initial to the direct use to the source demand manipulation, regeneration, reuse, carbon offsetting, and this also represent the holistic minimum carbon network. And for carbon offsetting, based on the 12.508 ton per hour we have identified, this can be reduced by tree plantation to achieve a 0 ton per hour of CO2 emission. And that's all for the overall case summary. Next, we will look into the design for the network diagram. Now, we'll look into the final network allocation diagram, NAD for the refinery, and also carbon distribution network design. Basically, from the level 3 H4, we have copy paste the source and demand data of the streams, and then we have created the stack bar chart for the sources and the demand streams so that we can visualize how much each source stream contribute to the demand streams to perform the exchange. And by visualizing this, we also can identify the exact amount of flow rate of CO2 for the each exchange. And this will help us to proceed for our next step, which is to do the carbon distribution network design. And for our refinery case, we have identified, as shown here, we have identified the fresh CO2 target of 29.248 and also the CO2 emission target of 12.508. And this is can be done based on the NAD diagram. And that's all for the video demonstration. Hope it will help all of you guys for the tutorial session in next session. Thank you everyone.